Okay, the next step in the lab was to disable auto summary. If we look at our routing table that we learned in certain situations, let's see what this one has to say about it. Oops. If we look at our routing table we learned, right? If we look at this case, it says RIP 192.168.22.0/24. Send that to 21.2. Well, we're not actually using 22.0/24. We have several, at least two subnets in the 22.0 network we're using. We're using 22.0/27, and we're using 22.252/30, but we only have one entry in there. And the reason we have that is because the RIP version 2's default behavior is to summarize those routing updates along classful boundaries. So what that means is if you're using a Class C, several Class C subnets, such as we are now, IP RIP, when you get the updates, those updates are going to come across as /24. So if we look at what comes across, if we look at what comes across, all of these updates we're getting on this router. All these updates we're getting on this router are coming across with a /24, even though we're not using a /24 anywhere. The only exception to that is the update we're getting from the bottom router on our FastEthernet 01. We're actually getting 11.0/27. And the reason we are getting that specific network is because the routers are smart enough to know, hey, I have a interface in that network. I can't summarize. We share an interface in that same network, so that router might be using that subnets of that Class C address space also. So I can't summarize that. So there are times when that could cause a problem. So you can disable that, which we are going to do by going under router RIP and typing in no auto summary. That will disable that behavior. We have to do it on all the routers. And once we do it on all the routers, we'll go back to that router we were on and see how it changes the updates we're getting. Oops. Same thing. So if we go back to our top router we're just on, look at our routing table. Now we see that we're actually getting the different subnets that we're using that we're learning from the other router. Here we're learning about a /30 and a /27 instead of just the /24s. So if we look at our debug output now, we should see the updates come across with the actual networks that we're using and not with just a /24. So does it matter if it's summarized or not summarized? Well, most of the time the answer is no. It's actually probably better to be summarized, because when it's summarized, that will make your routing table shorter and faster to search, because a routing table that has less entries is faster to search through. So it's usually probably better if you have it summarized. But there are some situations where if you have things addressed in a certain way that's beyond the scope of this discussion, it could cause problems. If you're interested in knowing about that situation, ask me in class and I'll tell you about it. So if we look at our update we're getting now, we're getting 11.0/27. So we're actually learning the networks and with the correct subnet mask in this case. So that was the auto summary part. The next part of the lab, we're going to create some failures and see how long it takes for the network to stabilize. When I say stabilize, that means that everything's back to normal. So Well, let me step back first. First, we're going to do some throughput test with the network and the state it's in. Then we're going to cause a failure. Then we're going to do another throughput test. I don't have a throughput tester within the simulator, so let's pretend we're doing a throughput test. Hey, run the throughput client on this side, the throughput server on this side. Run the test for a couple minutes, get a speed of how fast that's going to be going. Okay, we're done with that. So now I'm going to start a continuous ping on this PC. -T does a continuous ping. I have a continuous ping going, and I'm going to cause a failure on this router, and we're going to see how long it takes for the routing protocol to notice that the failure occurred and take care of that. I have this little fancy stopwatch I downloaded, so we'll use that to time it. So I'm going to shut down the serial interface again and see what happens as far as the routing protocol goes and how long it takes for it to notice. So it's down. I started the timer. Get my ping back up. So the ping went down just now. Where'd my stopwatch go? And now we're going to sit here and watch it for a little while and see how long it takes. Wow, that was pretty quick, surprisingly. About 15 seconds. In the manner in which we caused that failure, it came back in about 15 seconds. Does that match what the book said should happen as far as the time for a ping to come back for a RIP failure? Well, not really, right? The book went through all these different timers, the periodic timer and such, and said basically you send periodic updates every 25 to 30 seconds or so, and you have to mix like 6 of those before you take any action. So in theory, that was far too fast. In the lab, we're going to do another throughput test now, and it should be faster because it's going across the faster links. I'm going to bring this interface back up, and then we're going to cause another failure. The reason that failure was detected so quickly, was because the interface went down. When the interface goes down, the router knows for sure that it can't send packets out that interface, so it takes action immediately to fix the problem. If you just stop getting routing updates, you don't know what's going on, so you're like, hey, I didn't get any routing update, I'll just hang out and see what's going to happen a little later on. So we're going to create a scenario now where, actually I need to keep that down, because if I don't keep that down, then the packets are going to go across that link and nothing's going to happen. So let me bring that back down again. So now that link's down. And let's go up here and see which path it's going to be taking across. And we need to wait. I may not be able to simulate what I'm trying to simulate based on the way this is working right now. The way this is set up right now anyway. So we'll try. We'll see what happens. Another tool, another utility we didn't really talk about that we used to do in this lab, but I apparently took it out for some reason, was traceroute. When you run the traceroute command, it shows you the path your packets are taking across the network. We've done it before in class, but it's actually useful in this case too to look at the path our packets are taking. So in this case, it shows the IP addresses of the router that process the interface, and that'd be the IP address of the interface the packet goes in. So this 11.1 would be this interface on this router. 11.253 would be this interface on this router, and then it's going across the simulated gig link. 1.2 would be this interface on this router, and then 22.254 is going to be this interface on this router, and then 22.2 is this PC down here. So this is actually going across the simulated gig link right now, so that's not going to allow me to test in the way I wanted to unless I put another switch in there and then connect the switches. So let me try that. Let's see if that's going to work. No. So our goal here is to create a failure that is not a failure of the interface on the router. And there's gig peak ports. Let's connect those together. So in a couple seconds, when this spanning tree nonsense finishes doing what it's doing, my routing table should stabilize, and we'll see what it says the path is. Let's get the PC and do another trace route and see what route it's taking right now. Oh, it's not taking any route. That's awesome. That's so good. We can ping it though, so maybe now it's better. Yeah. So routing protocol is kind of slow sometimes. So it's going across a gig. So in this case, we may not get the desired behavior. Let's look at the routing table. 22.0. Yeah. So if we look at the routing table, essentially for 22.0, we have two equal cost paths. In this case, grip says, hey, you can either go this way or that way. So once I failed this link between the two switches, then it could automatically use this link because it knows it's there. In theory, if I had this set up some other way, it should take longer to fail. But let's see what happens, because I know what should happen, but or I know what I think should happen, but that's not always the case. Let's start my continuous ping again. Let's get my not my stopwatch yet. Yeah, I need to reset it. Reset, and then we're going to just disconnect this link between the switches. So what happens is this router doesn't know there's a problem, so it might still keep using the same old route. So we might lose every other ping because it just doesn't know any better. So let's see what happens. Start my stopwatch. Get my ping back up. So yeah, so we have a failure in our routing, which it failed twice and then switched over to the other link, maybe. Let's go to our routing table. Yeah, so it still has the route, it still has the bad route, 22.0. And if you look at this timer here, that's the time since the last update. So since I said we have updates every 25 to 35 seconds, once this gets past 35 seconds, you know you're missing updates. So let's see. Yeah, we're dropping a lot of pings in this case. So sometimes it's going the good way, sometimes it's going the bad way, because the router hasn't yet determined that the bad way is the bad way, if that makes any sense. So we're going to sit here about 3 minutes and wait until that all those timers the book talks about, the periodic timer, we got to miss about 6 of those updates before it does anything. So we will wait about 3 minutes. So if you want to fast forward this program for about 3 minutes, I'll just stopwatch up there until we get about 3 minutes, and we'll see what happens. Why are you still listening? I said fast forward. I'm not going to sing or anything to keep you entertained. Play some Jeopardy music. Yep, minute 152. So the last update you got was 1 minute 52 seconds ago. We're still probably sending packets the wrong way. Yeah, we still have a pretty terrible situation in our network. So this might actually be harder to figure out because you're getting some packets through, right? If we didn't have a link equal cost link. See, right now we have two links going the same cost. If we didn't have an equal cost link, all the packets would fail. So let's 223. Let's see what happens. $231. We still have it in there. Oh, check that out. Right around 3 minutes, it says it's possibly down. So now that it's possibly down, hopefully if we go back to our ping, it's not using it anymore, or at least we'll stop using it in the somewhat near future. So now that route is out of there. So now hopefully our ping's back. Maybe if I kill it and start over, it'll work better. Yeah, sometimes things in the simulator tool don't work as they should. At this point we have a route. Well, let's go look at this other router. It could possibly still have the old route and could be trying to route the packets back the wrong way. Let's see what it has for 11.0. Yeah, so this router still has the 11.0 network going across the gig link as being possibly down. So it might still be trying to use it. Which, if you thought it was down and you had another route, you would think it would just give up, right? So let's wait a minute. This possibly downness that's showing up is probably a factor of the garbage collection timer as discussed in the book. So you don't want to immediately delete routes as soon as you notice they're down, because you need to tell all your friends. Because in the past you were telling your friends, hey, I know how to get to 22.0, or I know how to get to 11.0. If you don't know how to get there anymore, you need to tell your friends, hey, I don't know how to get there anymore, so that your friends will know that you don't know how to get there anymore, so they stop sending the traffic to you. Because there are some issues that could be cause the 2-node and 3-node instability problems that the book talks about. If you don't do that. And how do you tell your friends you don't know how to get there anymore? The RIP, you send updates with a metric of 16. Basically 16 is infinity in RIP. So when you send updates of 16, that basically says, hey, that is down. Let's look at it and see if we can see an update being sent with 16 for the metric. So there's an update I received. Hopefully I'll send one and it'll have 16 for the metric. Metric being the hop count. Build sending. No. I am not sending an update with 16 in it, which is interesting. Interesting, but it makes sense now that I think about it. Because even though I can't use that particular route anymore, even though I can't use that particular route anymore, I still have a route to that network. So I'm not going to stop using that route. I can still get there from this router, just not using the link I was using before. So that could be unbug. That could be causing some of this weird behavior too. So let's see what my ping looks like. Hey, look, finally, did I stop the stopwatch? No. Nearly 7 minutes for it to finally stabilize in a reasonable fashion. So if I have a backup link connecting routers together that I want my traffic to go across when one link goes down, I don't think 7 minutes is an acceptable amount of time for it to take for my routing protocol to figure out, hey, that link's down and I want to start using this other link now.